Hi, hello to everybody. Good morning or good afternoon to everybody, depending on the area you are joining this webinar. So let's start today's webinar called LM2A Motor Control, Motors with Peripheral Encoder. So this is one of the new control modes we have included in the LM2A. Let's start by the aim of the webinar. First of all is to understand what means motor with peripheral encoder. So which are the characteristics of this motor, why this motor is more complicated than standard motors to be controlled, what to keep in mind, especially about feedback, about encoder, and then finally how we solve this with LM2A. So which kind of motor control we have to use, how do we do it, which are the rated parameters, and then how to start up properly the lift. So the contents, as more or less introduced in the aims. First of all, we're going to describe the motor characteristics. Then we are going to speak about encoder characteristics or the feedbacks, possible feedbacks we can find, speed feedbacks we can find connected to this motor. Then the inverter special settings, we are going to discuss only the basic parameters of the inverter plus the additional parameters for this new control mode. Then how to start the motor, how to perform the volt tuning. And then we will see some standard movements and where we can find normally problems and how to solve the problems. Okay. So here you have one motor example. Okay, so this is one of the motors you can find in the market with a peripheral encoder. First thing to mention about this motor is that it's a permanent magnet synchronous motor. This means that in this kind of motor, we have magnets on the rotor. And the way of controlling this kind of motors is by inverter applying a flux in front of the magnet and turning this flux. So it's very critical, it's very important first to find where is the magnet and then don't lose this position during the complete movement. Second critical point, as you can see, is that the encoder is placed outside, on the periphery of the motor, not in the middle of the shaft, where it's placed in all other synchronous motors you can find in lift industry. So let's now discuss or describe why we need a special mode, why this is complicated to control. So in the left side of the slide, you see a picture of the motor. And then in the middle, you see a small graphic describing the different parts. Okay. First of all, we have the pulley in the middle where the ropes, which are going to move the counterweight and the car, are placed. Okay. This pulley has a certain diameter, and this diameter will give the speed that the lift is moving at. Okay. Then we have a external wheel or external pulley that you can see on this graphic described by DS and the parameter L130. After all, after we discuss with the inverter parameters, we're going to describe about this parameter. We're going to speak about this parameter, okay? And finally, we have the encoder, which is placed in the top left side or right side of the motor, okay? So problems we have, as you can see here, as you can imagine, the speed that the encoder turns is not the same speed like the pulley, which is moving the lift. So they have two different speeds, and it's complicated. We have a tricky point here to control the motor when or where the speed feedback, the encoder is giving different speed than the ones we want to move the lift. Second, we have, well, as mentioned, we have two diameters. We have the pulley diameter and the outside diameter, okay? So this is another variable which makes the control a bit more tricky. And finally, the fixation point of the encoder is just a round rubber wheel, okay? We don't have teeth, we don't have any mechanic which fix strongly the encoder into the motor. This means that we can have some slip, and after a lot of motion, this rubber the diameter can be decreased because of the usage. Okay, so this is another variable which makes this
control of the motor more tricky. So at the end, summarizing, as mentioned, as introduced, we need a special control mode. As described, this is a synchronous motor, but a standard control for synchronous motors cannot be used because all these points mentioned before. And this is why we need a special control mode. Yeah, going back to basically the speed feedback, okay? As mentioned, as already introduced, some of those motors have incremental encoder, standard incremental encoder. There are different kinds of incremental encoders, but standard ones. This is okay for frenetic lift. We have option cards for this kind of encoder. So summarizing, frenetic lift LM2A is able to control this kind of motor with incremental encoders. But we find as well in the market motors with resolver. In this case, we have no option on the inverter to connect this kind of speed feedback, the resolver. Okay, so in this case, we ask you if you have in mind to make a retrofit of this system to change the resolver by an incremental encoder. So what to keep in mind regarding encoders? Okay, first of all, we have the encoder itself, the electronic. Okay, from this point of view, any encoder in the market can be used. Any incremental encoder in the market with line driver electronics or push-pull or open collector are okay to be used. Okay, but there are some other points which has to be kept in mind, and it is very important that it is solved properly. First one is the mechanical coupling. As you see here, the encoder must have a mechanical disc which allows the encoder to be fitted into the chassis of the motor. You see here the disc from the encoder shaft part and from the back part. Okay, so this is something which has to be solved properly, and that the encoder supplier needs to be properly solved. Yeah, they must have a proper solution for this. And the third part, as already introduced before, is the rubber wheel. This is a third part of this encoder equation, which needs to be solved as well. Okay, it has to be the proper rubber wheel. And yeah, as mentioned before, because of the usage, the rubber gets old, yeah, and then the diameter can change. So this is one part that after the time, this can be changed, or this should be changed in order to avoid problems. So where do we connect the encoder on the inverter? As you probably know, we have two option cards, OPC-PMPG for push-pull or open collector encoders that normally have a voltage range from 10 to 30 volts. And then OPC-PMPG for line driver encoders with normally a voltage range of, well, 5 volts. Yeah. How do we connect the encoders? So in case of PG3, in case of open collector or push-pull encoders, normally we are going to have, or it's enough for us to have A phase and B phase plus the supply. And the supply will come from the inverter, will come from the option card. So very basic, okay, very easy. A phase connected to the PA terminal on the inverter, B phase connected to the PV terminal on the inverter, and the supply positive part in the PO terminal and the negative part or the zero on the CM. Yeah. Shield is important, of course, that the encoder cable is shielded and the shield has to be connected in the ground. And then we have the connection of OPC-PMPG. In this case, we have the negative parts of A and B channels. Okay, so we are going to connect A channel in PA plus and PA minus, and the B part in PV plus and PV minus. Same for the power supply. Important point to keep in mind is that OPC-PMPG is an option card that can be used for different kind of encoders, a kind of absolute encoders as well. And by default, by factory default, the inverter has the wire break detection for the absolute part of these encoders that we are not discussing in this presentation. So in order to avoid that the inverter is tripping PG alarm because the wire is not connected, because in fact we don't need those wires, keep in mind to put the deep switch 2, so deep SW2, all the switches, the 4 switches you can find in on position. Yeah, otherwise, as mentioned, just supplying the inverter, you will face PG error. Okay, so let's move. Let's start now to discuss basic parameters, basic setting of the inverter. Okay, let's start by motor parameters. First of all, please remember, I'm sure you know that parameter C21, PO1, and FO3 has to be set in this order. Yeah, and it's important. It's important not to change the order because then the setting on the inverter can be corrupted. Okay, this is always important when you set the inverter by means of the keypad. When you use the loader software, it is handled by the loader software, so you don't need to keep in mind this. So let's start by defining C21, the speed unit selection. In this case, in this example, we show Hertz, so C2122, but as you know, as you remember, C21 speed units can be selected between RPMs, millimeters per second, and meters per minute. Then we have very standard motor parameters, PO1 motor pulse, PO2 rated power of the motor, and PO3 rated current of the motor. Then we have PO7 resistance on the stator of the motor. Yeah. By default, in the synchronous motors, in the standard control, we suggest 5%, which is more than enough because we perform the pole tuning always with a technician on site, which can make sure that everything is working properly during the pole tuning. But in this case, as I'm going to explain after, we base this control in an automatic pole tuning. So in order to avoid problems, in order to make sure that the inverter is able to find the right pole tuning every time that the pole tuning is automatically done, we recommend you to increase PO7 to 20. Okay. In case of doubt, you can always adjust the right value by performing auto tuning. Auto tuning, remember, it's in parameter PO4. So you select mode 1, where the inverter is just measuring the resistance and the inductance. In this case, you get the right value for PO7. Yeah. Then we have special parameters for this motor control. Additional motor parameters which makes the control of this motor a bit more easy because in the inverter we have a better image of the characteristics of the motor. Those are the parameters P60, P62, and P63. So the armature resistance, armature Q-axis reactance, and the interface inductive voltage. Okay. Not so much to mention about those parameters. Those are parameters that you can find on the motor nameplate. And yeah, you normally you should have, or you should put the setting on the inverter according to the motor nameplate. P65 is the saturation correction for the inductance because depending on the speed, depending on the voltage supply, the inductance can change. Okay, so we apply a saturation factor, which by default is set to 65, and this is normally okay. We don't need to touch this parameter. Then returning to the standard motor parameters, FO3, motor rated speed or the speed of the motor at lift speed. Yeah. FO4, motor rated frequency because C21 is set on Hertz. Okay. FO5, motor rated voltage. And finally, F42, set to 1, which is vector control with PG. Yeah. So in this case, we set the control mode as it was a standard synchronous motor. Remember that on the inverter, we have certain macros that can be selected in the parameter HO3, which pre-program the inverter with some basic setting, very useful for each kind of applications. So in this case, as we are speaking about the synchronous motors, the recommendation is always start by the default setting set on HO3 equal to. Okay, this is a good starting point. It's our recommendation. Then encoder parameters and pole tuning parameters. Okay, this here we have the first difference. Okay, LO1. LO1 is the encoder selection, and the option card we are going to mount. Okay, LO1 we are going to select 1. 1 means AB plus Z channel. So means that the inverter is going to use an encoder with AB plus Z channels. I forgot to mention before during the wiring of the encoder, but probably some of you have realized, we do not connect the Z phase. Even in LO1, we select encoder control with AB plus Z. This is something that the inverter is handling internally. So Z phase is not needed to be connected. Even though if you connect it, no problem. The inverter will just skip those signals and will not happen anything. LO2 pulses from the encoder.
This will depend, of course, depending on the encoder you mount. Normally, for this kind of applications, 1024 pulses per revolution is more than enough. If you want a bit better performance, especially on the rollback control, you can go up to 2048. But normally the experience says that with 1024 is more than enough. Okay. And then we have the LO7. On LO7, we activate and we select the type of pole tuning to be performed automatically. As mentioned before, for this kind of application, we will base the control in an automatic pole tuning. This means that in certain conditions, the inverter will perform automatic pole tuning before starting the movement to make sure that we start from the right position of the magnet. Remember, keep in mind, we are basing this control, we are using incremental encoders without absolute part. So in case of during a stop or in case of problems, the inverter is not able to read from the encoder, which is the absolute position. So this is why we need to perform automatic pole tuning. How to select where do we do the automatic pole tuning? Okay, this is done in the parameter L198, bit 5. In the recommended setting, you see bit 5 is set to 1 because we recommend to perform the pole tuning always at every start. So every time that the lift starts the movement, inverter performs a pole tuning to make sure every time we start from the right position of the magnet. Okay. You can disable this if you want, but our recommendation is always use the pole tuning at every start. If you disable this, then the inverter is going to perform the pole tuning at power on when the motor is moving because the brake is open, not because the inverter is controlling the motor, and when there is an alarm on the inverter. Okay, under those three conditions, the inverter is going to perform automatic pole tuning before a start. And finally, we have the specific parameters for the motor control. Okay, first of all, we have 130 and 131. On those parameters, we define the diameters mentioned before. So the shift diameter, the outside one, okay? In this case, it depends on the motor because depending on the power, the shift diameter will be bigger or smaller, okay? So depending on the power of the motor, depending on the motor you have in front, you have to measure and you have to set here the right external diameter. Please remember, not the inside pulley diameter. And then L131 is the encoder diameter, basically the rubber wheel diameter, which this one we know because normally this rubber wheel will always have the same diameter. This is 37.2 millimeters, okay? And then we have the parameters L132 and L133. This is theta compensation by band and gain lower limit, okay? As mentioned before, we have a synchronous motor with magnets. On the other hand, we don't have absolute encoder. So in one hand, we have an inverter which needs to control the motor by placing the flags in front of the magnet, so in a certain position. On the other hand, we don't have the right feedback or the right encoder to do this. This means that we need additional tools to follow the magnet position while the motor is moving. Yeah. So if you allow me this comparison, L132 and L133 is a kind of observer, which is monitoring while the motor is moving where the magnet is placed. If we detect or we feel that the magnet position is being loose because the torque, for example, increases, this theta compensation will react in order to try to find again the magnet position. Okay, so, and this is done online. So while the motor is moving, so L132, 45 degrees by default. This is the error we allow the inverter to have. So when we guess that we have lost magnet position more than 45 electrical degrees, after these 45 electrical degrees, after we see that the error is 46, 47, 48, we start to apply the compensation, and in 133 defines how fast, how strong we apply this compensation. Okay. So here you have an example of a motor nameplate.
Okay, and well, this is just to show that most of the parameters you need to set into the inverter appears on the motor nameplate. Yeah, so on the motor nameplate you have power, you have rated current, rated speed, rated frequency, but as well we have the special parameters we mentioned before about the interface voltage, the armor, inductance, and resistance. Okay, so as you see, most of the parameters can be found in the motor nameplate. In the motor nameplate, we find as well a shift diameter. Yeah. As you can see on the image, this is wrong diameter from the inverter control point of view. This is the shift diameter where the ropes are placed. Okay, remember that this diameter is not useful for the motor control because we need the external diameter where the encoder is mounted. Again, yeah, this diameter needs to be measured on site depending on each motor. Okay. And then the only parameter that we may not find in the motor nameplate, as you can see in this example, is the motor poles. Okay, but in this case, we have the formula. We have the rated frequency of the motor and the rated speed of the motor. We can calculate the number of poles. Yeah, it can happen that we're doing this formula, we find an intermediate value. So this means you know that always poles are per poles. So it would be 10, 12, 14, 16, for example. It can be that by the formula, we find that the motor poles are 15 something. Yeah, in this case, there is no other way to try both, to try 12 or to try 14, because those are the number of poles for sure motor has. So in this case, we have to do trial and error. Okay. Another option is to move the motor in BF control or in open loop control, like we explained in the webinar last week, and monitor the RPMs and the encoder pulses. So if we monitor the RPMs and encoder pulses, sorry, in a set frequency, so in a frequency we ask the motor to turn, we can as well find the motor pulse thanks to the same formula. Okay. So now we know the motor, we know the encoder, we know which parameters we have to set. So let's start the motor. Let's start the lift. Let's move the lift. Let's start by pole tuning. Here it's very similar like the standard pole tuning procedure, you know, but it's even more easy for the end user because of the automatic pole tuning. So point 1, point 2, and point 3 are the standard things you need to keep in mind that we have discussed in the previous slides. So of course, we need to properly set the inverter according to the parameters mentioned before. We have to make sure that the encoder is properly connected and that we are receiving the pulses. You know that in the inverter you have some menus where to check if we receive pulses from the encoder and if the encoder board is properly mounted. Make sure that the connection between the controller and the inverter is properly done. Make sure that the enable is properly wired. But I know you are advanced users, so you keep in mind all those points. Then we just need to basically put the lift in inspection and give run command. Thanks to the automatic pole tuning, the inverter will perform a pole tuning, and then directly, without removing the finger from the button, the lift will start to move. Yeah, if everything is properly set, normally the motor will start to move properly, yeah, in up or down direction. It's very important that we always monitor the output current because this will give us clues if the motor is properly controlled or not. If after giving run command, performing the pole tuning, you know we can recognize that pole tuning is being done because we hear some whistling sound coming from the motor. If after this and when the lift starts to move, we get directly over current error, now this normally means that the motor phases are not properly connected and we have to swap, for example, U and B phase. We can do this by hardware, by changing the cables, or we can swap. We can change the setting, sorry, on the parameter H190. By default is 1. Then if this happens, we have to set it to 0. H190 to 0 is an electronic way to swap motor phases. Okay. We have one question. Let me publish it. Have to go to question mode. Yeah, in case of P62 and P60 values are not mentioned, how to set these parameters? Well, as shown on the motor nameplate, you always have those parameters. Yeah, so I have not seen any case where these parameters are not mentioned. So don't worry about this. Those parameters will be always shown in the motor nameplate. Okay. Let's continue with the presentation. Okay, so pole tuning, perfectly done. Lift moving, great. So now, which are the tests we should make in order to make sure that everything is working as expected? So first of all, as we are in inspection, let's move the lift in inspection. Yeah, to be on the safe side, let's move the lift up and down the complete shaft in inspection direction. And this is, well, this is an image taken with a loader software with a real-time trace of a lift moving in inspection under this control mode. You see that the speed detected reaches a certain point, so this is the target speed. And then, well, we have output current and output torque, which is constant after we have the acceleration phase. Yeah. The small peak you see at the beginning of the graphic on the output current or the torque current is this the pole tuning. During this short time, the pole tuning is performed. Okay. I would like to take this chance to that we are speaking about loader software and real-time trace. Please note, if you don't know, that we have a YouTube channel, and on this YouTube channel we upload the webinars, but we have as well some tutorials. Okay. We have a special tutorial where we explain how to set the real-time trace function. It's very easy, and if you follow the video, for sure you will succeed. You have the link of this tutorial in the upper part of the webinar. So if you click on this link, directly you go to the webinar, to the tutorial. But please check it after the presentation, otherwise you don't listen to me. Okay. So let's move to the next presentation. Before we have another question, let me publish the question. We go to questions mode. Here, what should be the minimum value of pulse of incremental encoder? Good question. Well, basically, we have checked the standard encoders you can find in the lift industry. This means, as mentioned it before, most standard encoder used in incremental applications is 1024 pulses. Okay. In the market, of course, there are encoders with a smaller resolution. Normally, I remember 512. To be honest, we have no experience. Even I expect from the speed control point of view. So during high speed, creep speed, acceleration, deceleration, we are not going to have any problem. I expect to have problems during robot control if we go with the encoder with 512 pulses. Yeah, this is just a guess because to be honest, I have no real experience. But my experience is based on a standard control of induction motors with incremental encoder. If you go under 1024 pulses, you have problems to control the rollback. As mentioned before, if you want to improve the rollback, you can go up to 2048. In this case, you have more resolution, so it's going to be easier to control the rollback. Even sometimes this is not necessary. So let's say, summarizing, our suggestion is always moving this range of 1024 pulses and 2048. First reason, because those are very standard encoders in the market that you can easily find, and those are the prices accepted by the market. If you want to go with more pulses, probably the encoder becomes more expensive.
Okay. Thank you very much for the question. And let's go back to the presentation. Okay, and this here we see a classical problem we can find during the inspection test. If we move the lift in inspection, for example, from the top of the shaft until the bottom of the shaft at constant speed, we see that the output current, the output torque is little by little increasing, as you can see on the graphic. And normally this ends up with a OLU alarm, so overload alarm. Yeah, this means, of course, that the inverter is losing little by little the control of the motor. And well, this means that we need to change some parameters. We need to do some actions to correct this. Normally, we can solve this by adjusting properly the parameter L133. The default setting is 0.8, and our recommended setting is 0.2. Normally, the recommended setting is the one which works in most of the cases, but you can try by yourself. You can little by little decrease L133 from 0.8 to 0.6, 0.4, until you find the right setting for your application. Another way to fastly solve this problem is by increasing the maintenance speed. This control mode is very tricky at very low speed. It's very easy to lose the control of the motor at lower speed. And when I say lower speed, I mean speeds of 1 Hertz, under 1 Hertz, or between 1 and 2 Hertz. Okay. In this case, the recommendation, especially as well for maintenance, because you need to have a certain speed to be able to do maintenance fast, is to increase maintenance speed. A recommended setting for maintenance speed can be 3, 4, 5 Hertz. Yeah, this is a good setting on the maintenance speed. Okay. So after we have checked that under inspection everything works properly, then it's time to move to the normal. Yeah, so we set the lift in normal, and yeah, we move the lift up and down. We stop in different floors, and we see that everything works as expected. And by everything works as expected, I mean a graphic like this. So we have a reference speed going to high speed, decreasing to creep speed, and then stop. And then we have the detected speed, which is showing more or less the speed profile of the reference speed, and an output current which with a logic value. Logic value means, okay, if we are driving, a certain overload during acceleration, and then during constant speed, output current of a value similar to the rated current of the motor or even lower, not higher. If the rated current of the motor, or the output current is higher than the rated current of the motor, means that the system is not well balanced, or like we have some mechanical defects. But this is another topic. Yeah. Okay. And then now let's see which problems we can face. Yeah. This is one of classical problems. We have here the lift moving. We go to high speed. We control high speed without any problem. We decelerate, and when reaching creep speed, the speed starts to be slowly and not under control, so it increases. This makes the output current increase as well, and then we have overspeed alarm on the inverter. Again, this is another sign that the motor control is not correct. Again, we need to adjust the right parameters, the parameters which allows the inverter to keep the magnet under control. In this case, we go again to the parameter L133. Again, recommended setting is 0.2. And remember that the default setting is 0.8. So again, either you go directly to the recommended setting where we have experience, it has been always working, or you adjust by yourself by trying different values between this range. Another way to solve this problem, I mean, this problem can happen, for example, because the rubber wheel is old, so the diameter is wrong, or the link between the encoder and the motor through the rubber is not good anymore. So meanwhile, you don't find a replacement for the rubber wheel. The recommendation is to activate the pole tuning at every start, because again, if we perform a pole tuning every start, we are sure at which position we have the magnet. So under this movement, probably more sure we will not face any problem. Okay. And the last problem we can face is over voltage during acceleration profile. So here you see the lift starts to move, and when we accelerate during acceleration, the control is lost and we have a over voltage trip. Yeah. These kind of errors we have solved by increasing the P63, so the interface inductive voltage. So we give more voltage, so the inverter applies more voltage during this acceleration phase, and this keeps the control, the motor control under control, so we avoid the over voltage alarms. Okay. So basically, that's all about my presentation. Okay. We have seen all the points we wanted to explain to you. Actually, we have gone through application note. There is a document and an application note done by us where we explain step by step how to do this. Yeah, you can go to this application note if you have more doubts, or you can now ask the questions you want to make. So, do I need a special version of LM2A? Yeah, correct. I'm all the time speaking about new control mode, but new control mode doesn't mean a special software version. Okay. In other words, this function is included in the on the standard software of the inverter. So, an inverter you have in stock, an inverter you buy from us or from distributors will have this function built in. Okay, so you can check that all the parameters I've mentioned during the presentation are there. Okay, so no need a special software version. Do you have any table showing recommended setting depending on the motor? Yes, we have a table with all the motors we have put in service. Please contact us by email and we can send this table to you. So, and with all the recommended settings. Yeah. Do I need to set L130 and L131 if the encoder is mounted in the middle of the pulley? Correct. Yeah. These kind of motors, actually you can find these two configurations, that the encoder is mounted on the peripheria and that the encoder is mounted in the middle of the shaft. In this case, no, we don't have to set L130 and L131 because then we have a standard synchronous motor as we know in the lift industry. So the encoder is mounted in the right place, so we can use the standard control mode. We don't need to keep in mind anything explained in this presentation. Yeah, we can use the standard mode. Can I use speed loop gains to improve comfort? Yes, of course. The speed loop gains, L36, L37, L38, and L39 are, of course, active. And in this part, you can adjust them in the same way you adjust it with a standard control for synchronous motors. Okay, so in here, I have not explained anything because basically you have to use your own experience and you are already able to set these parameters because you have a lot of experience. So yeah, they are there and you can adjust them to improve the speed loop control. Let me repeat again here that as this is a synchronous motor, our suggestion is to start by the default setting of the inverter, setting HO3 equal to. Okay. Well, we have answered a lot of questions. I think there are no new questions coming, so let's finish here. Just briefly, let me mention that we have an email for technical doubts. This is technical.inverter@fujielectric-europe.com. When you send an email to this account, you are sending this email to all the department or all the European technical departments. So either myself or any of my colleagues will contact you, will answer your doubts as soon as possible. So please feel free to use this tool anytime you want. And that's all. Thank you very much for your time.